What is thermonuclear fusion? It is a powerful cosmic process. Light atomic nuclei come together. They combine to form a heavier nucleus. This combination releases a huge amount of energy. Think of it as nature's ultimate power source. It is the same process that makes stars shine brightly. Scientists around the globe want to harness this incredible power. It could truly change our world for the better. This is the grand dream of fusion energy for humanity. Fusion is very different from nuclear fission. Fission is the process used in current nuclear power plants. Fission works by splitting heavy atoms like uranium. This splitting action releases energy. Fusion, however, does the opposite. It joins light atoms, like hydrogen. This joining also releases energy, often much more. The power of the stars comes directly from fusion. Understanding this difference is key to understanding energy's future. It is the universe's preferred method for generating vast power. Why do we call it thermonuclear fusion? The thermo part refers to very high temperatures. Incredible heat is absolutely necessary for fusion to occur. We are talking about millions of degrees Celsius. This heat gives atomic nuclei tremendous energy. The nuclear part refers to the nuclei of atoms. These are the dense cores at the center of atoms. These nuclei must overcome their natural repulsion to fuse. The extreme heat makes this possible. Thermonuclear fusion is the ultimate energy source. It powers the sun and all the stars in the universe. Imagine bringing a piece of a star down to Earth. That is the ambition of fusion research. The quest to replicate this stellar fire is a grand challenge. It pushes the boundaries of science and engineering. If successful, it promises a future with clean and abundant energy. This journey is one of the most important scientific endeavors of our time. Atomic nuclei usually keep their distance. They are like shy dancers at a cosmic party. Most nuclei have a positive electrical charge. Similar charges repel each other. This is a fundamental rule of electromagnetism. So, two positively charged nuclei will naturally push each other away. This repulsive force is called the Coulomb barrier. It is very strong at short distances. Overcoming this barrier is the first step for fusion. Extreme heat gives these nuclei the energy they need. It makes them move incredibly fast. Think of a superheated gas called a plasma. In this plasma, electrons are stripped from atoms. This leaves behind bare nuclei or ions. These ions zip around at astonishing speeds. The higher the temperature, the faster they move. This speed helps them to overcome their mutual repulsion. They can get closer than they normally would. This kinetic energy is vital for the fusion process. High pressure also plays a crucial role in this fiery dance. Pressure squeezes the nuclei closer together. Imagine a very crowded dance floor. The chances of bumping into someone increase. Similarly, high pressure increases the density of the plasma. This means there are more nuclei in a given space. This increases the probability of collisions between them. In stars, immense gravitational forces create this pressure. On Earth, scientists must find other ways to achieve it. When fast-moving nuclei under high pressure get close enough, a new force takes over. This is the strong nuclear force. It is one of the four fundamental forces of nature. The strong force is incredibly powerful at very short distances. It is much stronger than the electromagnetic repulsion. If nuclei can overcome the Coulomb barrier, the strong force binds them together. This binding creates a new, heavier nucleus. And importantly, it releases a tremendous burst of energy. The Sun is a magnificent giant ball of hot gas. It is mostly composed of hydrogen and helium. Our Sun shines brilliantly, providing light and warmth. This constant stream of energy is due to thermonuclear fusion. Deep within its core, the Sun is a natural fusion reactor. It has been burning for billions of years, and it will continue to burn for billions more. Life on Earth depends entirely on this solar fusion. It is the engine driving our solar system. Deep inside the Sun's core, the conditions are truly extreme. Temperatures soar to about 15 million degrees Celsius. The pressure is also immense, over 200 billion times Earth's atmospheric pressure. These conditions are perfect for fusion. No material on Earth could withstand such an environment. The Sun's own gravity creates this intense pressure. It continuously crushes the material in the core. This creates the perfect crucible for nuclear reactions. These are the conditions we try to replicate. In this inferno, hydrogen nuclei, which are single protons, fuse together. This happens through a series of steps called the proton-proton chain reaction. 4 hydrogen nuclei eventually combine to form one helium nucleus. The helium nucleus is slightly less massive than the 4 original hydrogen nuclei. This tiny difference in mass is converted into a huge amount of energy. This conversion follows Einstein's famous equation E = mc2. This energy is what powers the sun. This released energy slowly makes its way outwards from the sun's core. It travels through the radiative zone and then the convective zone. Finally, it escapes from the sun's surface, the photosphere. This energy streams out into space as light and heat. A small fraction of this energy reaches Earth. It warms our planet, drives our weather, and allows plants to grow. Without the sun's fusion, life as we know it could not exist. We live thanks to a distant, giant fusion reactor. Our sun is just one star among many. Our galaxy, the Milky Way, contains billions of stars. And there are billions of galaxies in the observable universe. Each of these distant pinpricks of light is a star. Most of these stars are powered by the same process, thermonuclear fusion. They are all giant fusion reactors, scattered across the vastness of space. These stars light up the cosmos. They are the universe's celestial beacons. Fusion is a truly universal phenomenon. All these stars are born in stellar nurseries. These are vast clouds of gas and dust. Gravity slowly pulls this material together. As the material clumps, the core heats up. Eventually, the core becomes hot and dense enough for fusion to begin. This marks the birth of a new star. Hydrogen fusion ignites, and the star starts to shine. This process is happening constantly throughout the universe. New stars are always being formed, powered by fusion's fire. Different types of stars fuse different elements. Younger stars, like our Sun, primarily fuse hydrogen into helium. This is the most common type of fusion. However, as stars age, they can evolve. More massive stars have hotter cores. They can fuse heavier elements. For example, they can fuse helium into carbon, then carbon into oxygen, and so on. This process is called stellar nucleosynthesis. It creates many of the elements we find in the universe. When very massive stars run out of fuel, they can explode. This is a spectacular event called a supernova. During a supernova, even heavier elements are forged. Elements like gold and uranium are created in these cosmic explosions. The intense heat and pressure of the explosion allow for rapid fusion of many nuclei. So fusion is not just an energy source, it is also the universe's element factory. Most elements heavier than hydrogen and helium were made inside stars or supernovae. Section 5. The promise of a star on Earth, limitless energy. Imagine harnessing the power of a star right here on Earth. This is the incredible promise of fusion energy. If we can build a miniature star, a controlled fusion reactor, it could power our entire civilization. This technology could solve many of the world's energy problems. It represents a monumental leap forward for humanity. Scientists and engineers are working hard to make this dream a reality. The potential benefits are truly transformative for our future. One of the biggest advantages of fusion power is that it is clean. The primary fuel, hydrogen isotopes, produces helium as its main byproduct. Helium is a harmless inert gas. It does not contribute to greenhouse gas emissions. Unlike nuclear fission, fusion does not produce long-lived, highly radioactive waste. While some reactor components may become activated, this radioactivity is shorter-lived. This makes fusion a much safer and more environmentally friendly option for the long term. The fuel for fusion energy is also incredibly abundant. The main fuels considered are deuterium and tritium, which are isotopes of hydrogen. Deuterium can be extracted from ordinary seawater. There is enough deuterium in the oceans to supply energy for millions of years. Tritium is rarer, but it can be bred from lithium. Lithium is also a relatively common element found in the Earth's crust and seawater. This means fusion offers a virtually inexhaustible energy supply. This near-limitless supply of clean energy could reshape our world. It could end our dependence on finite fossil fuels like coal, oil, and gas. This would significantly reduce air pollution and combat climate change. Abundant energy could also help desalinate water, produce hydrogen for transport, and power industries. It could lift nations out of energy poverty. The prospect of fusion energy offers hope for a sustainable and prosperous future for all humankind. Section 6. Fuel for the future, deuterium and tritium. The most promising fusion reaction for power plants on Earth involves two special types of hydrogen. These are known as isotopes of hydrogen. Isotopes are atoms of the same element, but with different numbers of neutrons. The two isotopes for fusion are deuterium, also known as D, and tritium, known as T. The deuterium-tritium reaction, or DT reaction, is favored by scientists. This is because it can achieve fusion at lower temperatures compared to other fusion reactions. It also releases a substantial amount of energy. Deuterium is a stable isotope of hydrogen. Its nucleus contains 1 proton and 1 neutron. It is found naturally in water. About 1 in every 6,400 hydrogen atoms in seawater is deuterium. This may seem like a small fraction. However, the Earth's oceans are vast. This means there is an enormous amount of deuterium readily available. Extracting deuterium from water is a well-understood and relatively inexpensive process. This makes deuterium an abundant and accessible fuel component. Tritium is another isotope of hydrogen. Its nucleus contains 1 proton and 2 neutrons. Unlike deuterium, tritium is radioactive. It has a relatively short half-life of about 12.3 years. This means it does not occur in significant quantities naturally. However, tritium can be produced. It can be bred inside the fusion reactor itself. This is done by bombarding lithium with neutrons released during the DT fusion reaction. Lithium is an abundant metal found in rocks and seawater. The DT fusion reaction works like this. A deuterium nucleus fuses with a tritium nucleus. This fusion produces 2 particles. One is a helium nucleus, also called an alpha particle. The other is a high-energy neutron. The helium nucleus carries about 20% of the energy released. The neutron carries about 80% of the energy. This energy, particularly from the neutrons, can then be captured. It can be used to heat water, produce steam, and drive turbines to generate electricity, just like in conventional power plants. Section 7. The Herculean task taming the Sun's fire. Replicating the conditions of the Sun's core here on Earth is an immense scientific and engineering challenge. It is truly a Herculean task. To achieve fusion, we need to heat the fuel to extraordinary temperatures. We are talking about temperatures exceeding 100 million degrees Celsius. This is many times hotter than the core of the Sun itself. Creating and maintaining such extreme temperatures is one of the biggest hurdles. It requires sophisticated technology and incredible amounts of energy input initially. At these extreme temperatures, the fuel exists as a plasma. Plasma is often called the 4th state of matter, after solid, liquid, and gas. In a plasma, atoms are stripped of their electrons. This creates a superheated soup of ions and electrons. The challenge is that no known physical material can withstand direct contact with the plasma at 100 million degrees. Any container made of metal, ceramic, or any other substance would instantly vaporize. So we cannot simply build a physical box to hold the plasma. To solve this containment problem, scientists use powerful magnetic fields. These fields act as an invisible magnetic bottle. The charged particles in the plasma, ions and electrons, are affected by magnetic forces. They spiral around the magnetic field lines. This allows the plasma to be held in place suspended in a vacuum. It is kept away from the walls of the reactor vessel. This technique is called magnetic confinement. It is the leading approach in fusion research today. It is a delicate balancing act. However, keeping the plasma stable within this magnetic bottle is extremely difficult. Plasma is a very complex and dynamic substance. It can develop instabilities, much like how smoke swirls and billows. These instabilities can cause the plasma to escape confinement, or they can cool it down, stopping the fusion reactions. Scientists are constantly working to understand and control plasma behavior. They use advanced diagnostics and sophisticated control systems. Achieving sustained stable plasma confinement is key to practical fusion power. Section 8. Pathways to power. Tokamaks and stellarators. Scientists around the world are exploring several different designs for fusion reactors. The 2 main types of magnetic confinement devices are tokamaks and stellarators. Both aim to create and contain the superheated plasma. However, they achieve this using different configurations of magnetic fields. Each design has its own advantages and challenges. International collaboration is crucial in developing these complex machines. We are learning more with each experiment. Tokamaks are currently the most widely researched design. The word tokamak comes from a Russian acronym. It stands for toroidal chamber with magnetic coils. A tokamak has a donut-shaped or toroidal vacuum chamber. Powerful magnetic coils surround this chamber. These coils create a strong toroidal magnetic field that runs around the donut. Another set of coils induces a large electrical current within the plasma itself. This current also generates a magnetic field, helping to confine and heat the plasma. ITER, being built in France, is a giant tokamak. Stellarators are another type of toroidal device. However, they have a more complex, twisted and three-dimensional shape. Unlike tokamaks, stellarators generate the entire confining magnetic field using only external coils. These coils are intricately shaped and precisely arranged. This design means stellarators do not need a large current flowing in the plasma to maintain confinement. This could make them inherently more stable than tokamaks. However, designing and building these complex magnetic coils is a significant engineering feat. Wendelstein 7X in Germany is a leading stellarator experiment. Besides magnetic confinement, there is another major approach called inertial confinement fusion, or ICF. ICF works on a completely different principle. It uses extremely powerful lasers or particle beams. These beams are focused onto a tiny pellet of fusion fuel, typically deuterium and tritium. The intense energy rapidly heats and compresses the pellet. This creates the necessary conditions for fusion for a very brief moment, before the pellet blows itself apart. The National Ignition Facility, or NIF in the USA, is a major ICF research center. Each pathway has unique hurdles to overcome. Section 9. Conclusion. The Stellar Dream. Challenges and Triumphs Ahead. Thermonuclear fusion is the universe's primary energy source. It is the engine that makes stars shine across the cosmos. This remarkable process involves light atomic nuclei combining. They merge to form heavier nuclei, releasing astonishing amounts of energy. From the hydrogen burning in our sun to the creation of heavy elements in supernovae, fusion shapes the universe. Understanding this fundamental process allows us to comprehend the workings of stars. It inspires us to reach for new frontiers. The quest to harness this stellar power here on Earth is one of humanity's greatest scientific endeavors. The potential rewards are truly immense. Fusion promises a future with clean, safe, and virtually limitless energy. It could free us from our reliance on polluting fossil fuels. It could combat climate change and provide abundant power for generations to come. This is not just a scientific curiosity, it is a vital mission for the future well-being of our planet and civilization. However, the challenges on the path to fusion power are equally vast. We must achieve and sustain temperatures hotter than the sun's core. We must confine and control a superheated plasma using complex magnetic fields. We need to develop materials that can withstand the harsh reactor environment. Building stable, efficient, and economically viable fusion power plants requires breakthroughs in physics and engineering. These are formidable obstacles that demand ingenuity, perseverance, and significant investment. Yet, despite these challenges, steady progress is being made. Decades of research have brought us closer to realizing the dream of fusion energy. International collaborations like ITER are pooling resources and expertise. New experiments are pushing the boundaries of what is possible. Each small triumph brings us a step nearer to our goal. The journey is long and difficult, but the promise of a star on Earth continues to motivate scientists worldwide. Thermonuclear fusion could indeed reshape our future, ushering in an era of clean energy abundance.